Okay, we're going to continue on here. We're talking thermodynamics here, chapter 16, I think. So again, as we talked about, thermodynamics is the study really of whether or not a lot of times what we're looking at in this chapter sort of will a reaction be spontaneous or will it be non-spontaneous? And again, as we talked about previously, remember that when we talk about something being spontaneous, again, that really has not too much to do with how fast or slow the reaction takes place. It just means that under those conditions, if you let everything just kind of be, you would expect this reaction to sort of take place. Now, again, you can have a spontaneous reaction that's very, very quick. You could have one that's very, very slow. You could have one that's, in between. But again, when we talk about spontaneity, that again is what we're looking at is, just whether or not under these particular conditions, this reaction should take place. Remember that when we look at the kinetics, for example, of a reaction, that's sort of where we look at how fast or slow the reaction is taking place, like we did at the beginning of the semester. We also saw that although the change in enthalpy helps in terms of spontaneity, it doesn't necessarily guarantee it. So you can have obviously a delta H that's exothermic and a delta H that is endothermic. And you can still have a spontaneous reaction occur in either case. Although an exothermic reaction will sometimes help with spontaneity because, again, you got a lot of energy sort of happening and that helps things starting to get together. Again, doesn't guarantee that your reaction will be spontaneous. So again, we talked about the change in entropy, which is this guy. And remember that the change in entropy has to do with the disorder or, again, order, whichever way you want to think about it. And it is, again, a little bit different than maybe how we normally think about things. If the amount of disorder actually increases, we will actually see a more positive sort of representation for the change in entropy. If the amount of disorder decreases, which by in turn means that the amount of order has increased, our delta S here will be negative and become more negative. Now we could calculate again the delta S of the universe, and that is comprised of the delta S of the system, which again is typically your reaction, plus the delta S of your surroundings. And again, we always sort of think about in terms of thermodynamics and sort of things transferring from one place to the next. We have sort of our system, and again, everything outside of that is our surroundings. And things like energy or heat can flow, in or out, depending on which direction you're sort of looking at. Now, if you do calculate the delta S of the universe, and again, it is a positive number, that means that that reaction should be spontaneous. So with that being said, we talked about how to calculate the delta S of the system or the reaction. We take our delta S of our products and we subtract the delta S of our reactants. And this is typically, you would go to the table, you would look up all the values there as normal. When we go to that table, we want to make sure that we get the right substance and also the right state for each of those. We also have to multiply by the coefficients in the equations when we do that. We could calculate the delta S of the surroundings by taking minus the delta H of the reaction divided by the temperature in Kelvin. Remember that the negative here is important for sort of that opposite relationship that occurs in either sort of an exothermic or endothermic type process with the surroundings. As we talked about under normal conditions, if you have an exothermic reaction, the heat's going to be leaving the system to the surroundings. And under kind of normal conditions or temperatures, that added heat and energy is going to increase the amount of entropy in the surroundings. And again, our delta H would be negative in that case. So two negatives will turn our delta S for our surroundings into a positive number, which means it's increasing the amount of disorder. Obviously, the opposite would be true if we had a more endothermic type process. Energy would be coming in from the surroundings to the system. And at that point, our delta H would be positive. Positive and negative will give us a negative for our surroundings in that case. As they are losing energy, they're going to slow down and become a little bit more ordered, a little less disorder. As they lose energy, they're not going to be like flying around as quickly. So they're just going to kind of slow down, and that's going to increase the amount of order is going to happen. Now we can obviously add both of these together, and we can see if our delta S of our universe is positive or not. If in the equilibrium process, it will equal 0. And again, the idea there is in an equilibrium process, we have forward reaction and reverse reaction sort of happening at the same rate. So there's kind of like a net no change happening anywhere because it's kind of keeping everything balanced in that sense, and it will equal 0. Now, we do also want to be careful with units, especially in this case, because probably you're going to have that number in kilojoules. You will end up with joules with this one. So when you do go into this equation here, again, you want to keep careful of those units so you're not off by a factor of like 1,000 or anything like that. We then moved on to sort of delta G, which is Gibbs free energy, and that is energy available to do some type of work. And we saw a few or a couple of different equations that have delta G in it. We have our normal sort of one, like all the other sort of thermodynamic properties. We could calculate the delta G of the reaction by just simply taking the delta G of our products minus the delta G of our reactants. And again, this would be a situation where you're just given the equation. You're pretty much going to go to that thermodynamics table and you will look up the values like pretty much you do with delta H and you do with delta S, and you can do with delta G as well. When we do calculate delta G, though, we can use it to determine spontaneity. So if our delta G value there is negative, it should be a spontaneous process. And if our delta G is positive, it will be a non-spontaneous process. In this sort of application, if it is a spontaneous process, the way the reaction is written, we would assume that the reaction would be proceeding from reactants to products in that case, if it is spontaneous. If it is a non-spontaneous reaction, we would assume the opposite there, that it's probably just going to hang out on the reactant side, not much is going to the product side, and we would have mainly reactants there with this reaction. I think we closed with another sort of delta G sort of equation here, minus T delta S. And this one for sure, you want to watch out on those units of both of those things, the H and the S. Remember that you can sort of look at this equation or think about this equation, and depending on whether your delta S is positive or your H is positive or negative, you can make some predictions as to what type of temperature, for example, you might need for a reaction to be spontaneous. So for example, if our delta H is negative and our S is positive, that's a pretty good combination for a reaction being spontaneous, because pretty much any temperature you pop in there, you will get a negative value for delta G. So that's really good for, a spontaneous sort of reaction. Now, if you happen to have delta H and a negative delta S, that's going to turn the back part of that into a positive number. And it will still be spontaneous at lower temperatures because delta H is about 1,000-fold higher than delta S. But if you get to really high temperatures, that's where the back part could kind of overtake the front part. And at high temperatures, you would expect perhaps a non-spontaneous reaction to occur. Now, if you had a positive delta H and a negative delta S, that negative again is going to turn the back part there into a positive, and that's two positives. And no matter what you do at that point, you're going to probably get a non-spontaneous reaction to occur. So you kind of think about this equation and think about sort of scenarios. And a lot of times in this chapter, they'll ask you those type of questions. They won't really give you like, numbers per se. Like I said, they'll go, hey, this guy's positive, this guy's negative at like high temperature, low temperature, would you expect sort of this reaction to be spontaneous? What equation you should use in terms of specifically, I would say with delta G is, as I mentioned last time, you might want to use whichever one sort of fits the information that's given to you. So if you're just given the equation and nothing else and you need to calculate delta G, then you should go to the table and do the products minus reactants. If you're given the H and the S, then you probably should go into that equation. Any questions on any of that stuff there? All right. So I think this is where we left off. All right, so if we look at this reaction here, a little decomposition reaction of calcium carbonate, It will form some calcium oxide and some carbon dioxide. The delta H for this reaction is 177.8 and the delta S is 160.5. Why don't you first calculate the delta G here at 25 degrees and determine, is this reaction spontaneous or not? So take a few moments there and calculate up delta G and see if it's spontaneous. See here, this situation, we have H, we have S given to us, so clearly the equation that has both of those would be a good one to use. We'll convert our temperature into Kelvin by adding 273, so it's going to give us a 298 here. Putting into our equation here, our delta G will equal our delta H, which is 177.8. Once again, as I probably did last time, I'm going to multiply by 1,000 here to convert it to joules. So again, I have the units the same. You do, again, need to do some type of conversion between the H and the S to get them into the same units. If you want to go into kilojoules on both, you can as well. We're going to go minus our T, which is 298 Kelvin, times our S, which was 160.5 joules. Putting all that together there, that's going to give us a 177.8 times 1,000 minus 298 times 160.5. It's going to give us about 129971. These are units of joules because I did obviously multiply by 1,000, convert to joules, and that's roughly about 130 kilojoules, right? If we do a little bit of rounding, divide by 1,000. First off, any question on the calculation? This reaction is spontaneous, non-spontaneous at 25. This reaction is going to be non-spontaneous here at 25 degrees, as we got a positive value for delta G. This is also a situation where if you maybe determine that this reaction would be non-spontaneous, for example, here at 25 degrees, we could also sort of use this equation to figure out at what temperature this reaction might become spontaneous. And we could do that because we know that the delta G does need to be negative. So if we set the equation equal to 0 equals our delta H minus T delta S, we can rearrange and solve for our T, and that would give us T delta S equals delta H, solving for T on the other side there, or solving for taking delta S to the other side will give us that our delta H over our delta S will equal our temperature. Now, if we put our numbers in here, we will end up with our delta H, which once again, we do have to watch units. So I'm going to multiply by 1,000 to get me to joules. Again, divided by my 160.5, which is already in joules. And that's going to give me something like, if I do a little bit of rounding here, 1,108 Kelvin, as that is joules per Kelvin there. And if I subtract 273 from it, that will give me roughly something like 835 degrees Celsius. Now, 835 degrees Celsius in this case of this reaction would be kind of like the minimum temperature that would be needed to turn this reaction spontaneous. First off, any questions on that calculation there? Now, if we think about what we had going on in this original equation here, we had a positive delta H and a positive delta S, which means the only way the back end here, which is the negative part of that formula, can beat the front part is we need a really high temperature. And I would say that would classify as a very high temperature, which would be needed for this reaction to become spontaneous. 25 degrees, kind of normal temperature, is not going to be enough in this case to overtake the front part there because of the entropy value there. Any questions on that? That's also what we see when we look at this graph. This is a graph of the partial pressure of CO2 versus the temperature. And remember that since CO2 in this equation here is the only gas present, The only way to get that gas is the reaction actually has to take place. So the reaction actually has to take place to make products in order for us to have pressure. And we actually see that right there on the graph, that right around 835, that is where we really start to see pressure occurring. Now, you may look at that and say on the graph, it does look like it does kind of get some pressure before 835, and you're correct. But at 835, it hits the magical number of 1 atmosphere. Our standard pressure is sort of where we'll get that kind of standard pressure type conditions occurring. So this equation here, or formula here, is really helpful. Obviously, if you have the H or the S, you could use it just simply to figure out whether or not the reaction will be spontaneous or non-spontaneous. But if you happen to hit an issue where your reaction is non-spontaneous, you could also use it to figure out at what temperature you perhaps need to make it into a spontaneous reaction. Any questions on any of that there? All right, so I'll try this one here for the following reaction. Delta H is, thank you, minus 1204. Delta S is minus 216. Are the reactants or products favored here under equilibrium conditions? So let's take a look at this one here. We have our delta G is equal to our delta H minus T delta S. And once again, we're going to use this equation because, frankly, that's the information that was given to us. So once again, we do want to watch our units here. So we're going to take our minus 1204. And once again, I'm going to multiply by 1,000 to get it into joules. Minus our temperature, which we do need to convert into Kelvin here, which is 298. And our S, which is minus 216.4 joules. Popping in our numbers there are going to give us minus 1204 times 1,000 minus 298 times minus 216.4. That's going to give us here. Try it again. Minus 1204 times 1,000. Probably helps to hit the right numbers. Try that one there. Minus 216.4. There we go. All right, we got minus 1139512.8 joules. That's a lot of numbers. We'll divide by 1,000 to put it into kilojoules. So negative like 1140 kilojoules. Seem good. This reaction should be spontaneous, right? As we did hit a negative delta G, which means we should expect this reaction to proceed in the forward direction towards our products, which means we should expect products there to be favored at equilibrium. Any questions on that one there? All right, so let's talk a little bit about free energy that phase changes, and a couple of things as we might talk about a little bit earlier. Remember that as we do transitions from phases, as we go from solid to liquid, liquid back to solid, that is a transition that occurs at the normal melting point or say freezing point of a substance. For example, for water, that is our classic 0 degrees Celsius as to where that occurs. Once again, as that occurs, it is a kind of have both phases happening at the same time. So you kind of have like ice crystals in the case of water at exactly 0 degrees Celsius. Again, it's not to get a little bit above or a little below zero that you kind of fully transition into the proper phase. There is, as we also talked about, I think earlier in this chapter, a certain amount of energy required to do that transition. And that is what is known as the delta H of fusion. And delta H of fusion, or the heat of fusion is sometimes referred to, is the energy that's required to do nothing more than take a substance from, say, solid to liquid, not changing the temperature or anything like that, but just the energy required to do that phase change, and also going in the other direction as well. So for water, something like that, the delta H of fusion is something like 6.02 kilojoules per mole, or roughly 335 joules per gram. It is the same number, regardless of sort of which way you're going in terms of the transition. If you're going from solid to liquid or liquid to solid, the sign is just different depending if it's an exothermic process or an endothermic process. So remember, as you go from solid to liquid, that is an endothermic process. And that would be in the case, say, of water, it'd be a positive, like 335 joules per gram or 602. Going in the opposite direction as we go from liquid to solid, we have to release that amount of energy to allow everybody to come together, and it would be negative, for example, 335 joules per gram. We have a similar situation that occurs as we transition from liquid to gas or gas back to liquid. And that happens at the normal boiling point of a substance. And obviously for water, as you probably should know as well, it's 100 degrees Celsius as to where that occurs. Once again, that transition does occur at the exact same temperature, not until you fully get above 100 degrees or below 100 degrees that you have sort of fully transferred in there. Just like the other transition, there is an enthalpy of vaporization, which is sometimes referred to as the heat of vaporization. And that is what is required to sort of do that transition. For water, it's something like 40.6 kilojoules per mole, or roughly 2,260 joules per gram is the amount of energy required to do that transition. It's kind of the same idea as you go from liquid to gas in this case. It's an endothermic process, so it would be positive 2,260 joules per gram. And as you go the opposite way around, there is going to be exothermic, which means we do need to release 2,260 joules per gram. So when we have these sort of transitions of phases, we also can see a change in the entropy as we go from one phase to the next. So when we go from one phase to the next, we could actually calculate the delta S, for example, of vaporization. We could also do something like the delta S of fusion, as well as you're sort of transitioning as you go from one place to the next. We could do this because this is an equilibrium process. That means in this case, our delta G will equal 0. And we could rearrange this equation and actually solve for, as we bring this guy to the left, we could solve for, as we see there, the delta S is equal to delta H over T. So this rearrangement of this equation here is the equation that I was talking about last time, that you should not confuse with the delta S of the surroundings. And the delta S of the surroundings is minus delta H over T. That one has the negative. This one does not, because it is derived from this equation. So again, if you're doing delta S of the surroundings, you need that negative to give that opposite relationship as we talked about as the energy flows from in or out of the system. Here, we don't have that negative, and it's a very common mistake that people will always throw the negative in with it because they remember the other formula. So if you're sort of doing this sort of phase transition where you're trying to calculate something like the entropy of vaporization or fusion or condensation, whatever it may be, you will not have the negative in there. So that's really important here. So here, our temperature does need to be in Kelvin as well. And if we do this for this transition going from liquid to gas, we have our delta H up here, and this is our delta H of vaporization for water. Water's boiling point is 100 degrees Celsius, which means if we add 273 to it, that is where the 373 comes from. That is the boiling point of water in Kelvin. And if we do that, we end up with a delta S, which is the entropy of vaporization for water of 109 joules per gram. So this also makes sense if we think about it. As we go from liquid water to gas, we are creating a lot more disorder, right? And that means that we should expect our delta S here, in this case for vaporization, to be a positive number, because we should see an increase in the amount of disorder that's happening here. Questions on that there? Now, what happens if I was actually doing the condensation move, where I went from, say, gas back to liquid in this case? what is the only thing that would change in this calculation if we were, say, doing like the delta S of condensation in this case? The only difference should be this number, which is the heat of vaporization, would then be exothermic, right? As we're releasing the energy. And that means it should be negative in this case, right? Still going to happen at the exact same temperature. And that would get us a negative 109 joules per Kelvin. And that also makes sense if you're going from gas back to liquid. You're going from gas where there's a lot more disorder happening to liquid where there's a lot more order. And we would expect the entropy change to be negative in this case. So again, the signs here do matter in terms of which way you're going. Also matters obviously in terms of using either the negative as exothermic process or an endothermic process. You could do a similar calculation down at the transition between solid to liquid or liquid to solid. You would use obviously the heat of fusion in that case rather than the heat of vaporization. Also a reminder that when we talk about these numbers of like 2260 or 40.7 or 335, those are specific for water. And that's also when we talk about 0 and 100, that's specific for water. So if you're doing some other substance, it will probably have a different boiling point, freezing point, and different heats of vaporization and heats of fusion as well. Any questions on that there? Uh, you mean here? No, so this is the process. So none of these equations are the surrounding in a sense. We're talking about just the actual system, and it's actually the phase change of the substance, for example, for like ice, for example, or a liquid water going to steam, basically. So we're talking about the actual system, which is why we don't have that negative in there, what we saw earlier on. And it's really because what we're looking at in this situation is actually this equilibrium process, and it's coming from that equation. So it's negative here because in the process of condensation, we're going from gas to liquid, and we're going from gas molecules that are flying around, which means it actually has to lose that energy, right? And that means it has to give off that energy in order for them to kind of slow down and come together into the liquid phase. And overall, the process of enthalpy in this case would be a negative process. And that's different than sort of the first one that we looked at where we're going from vaporization, which is going from liquid to gas. The liquid has to gain all that energy, right? And that's what allows it to really escape the liquid phase and go into the gas phase. And that's an endothermic process here. So that's sort of where the negative comes from. On the bottom one is because we're doing the process of going from gas back to liquid, where overall the enthalpy change will be negative. Other questions? So why don't you try one here? The enthalpy of vaporization for mercury is 58.5, and the normal boiling point is 630 Kelvin. What is the entropy of vaporization for mercury? Okay, so if we look at this again, this transition is going to happen in an equilibrium sort of process, which means when we look at our equation here, this delta G is going to equal 0. And that is really how we're going to get to our sort of rearranged equation where we could solve for our delta S, which in this case would be our delta S of vaporization, which would be our delta H over our T. In this case, our temperature is already in Kelvin, so not too bad. I'm going to take 58.5. I'm also going to multiply it by 1,000 because typically speaking, delta S is given in joules, so that's what I'm going to end up with, hopefully. And we got our 630 Kelvin in this case. And that will get us here 58.5 times 1,000 divided by 630. It'll give us something like 92.9 joules in this case. It is a positive number, which means it is going to increase the entropy of what's happening as we go from liquid in this case, again, to gas. You could probably safely assume that it is talking about going from liquid to gas, unless it really specifies something like you're going from gas to liquid. So usually we'll say something about condensation if it's kind of talking about going in the other direction or something should be mentioned about that. Once again, if we were doing sort of the condensation move here, really the only difference is that top number would now be an exothermic number and should have a negative, which would then turn our delta S into a negative, which would be more order. Here we are creating more disorder, obviously, as we go from liquid to gas. Any questions on that there? And if you didn't convert it to joules here, you'd have 0.092, I think, kilojoules. So let's talk then about our good friend equilibrium, because we really can't go too far without the equilibrium sort of guy. And a couple of other equations which are sort of important involving delta G. So adding to our growing delta G equations here, we have this guy right here. So in this case, we have our delta G is equal to delta G naught plus RT natural log of Q. So remember that when we see the little naught sort of symbol there above something, that oftentimes means those standard sort of conditions. So you could think of this delta G as like under non-standard conditions. So that would be our Gibbs free energy under some type of non-standard conditions. Remember that standard conditions basically means that we have 25 degrees Celsius as our temperature. If we're dealing with any type of molarities, they all should be 1 molar. If you're dealing with any type of pressures, they all should be 1 atmosphere. I would say in most cases, probably the concentration or the pressures are the things that would be sort of non-standard. So if you see a problem where they do give you pressures or concentrations and they're not all 1 molar, then that's probably where you would want to kind of use this equation. The rest of this is sort of normal fare here. Our R's are gas constant. It is the one with energy, so that's 8.314 Kelvin per mole. Our T is our temperature that does need to be in Kelvin, probably like normal. And our Q is our same Q that we've seen in multiple places throughout some chapters. That's our reaction quotient, which again is calculated the exact same way as you would calculate K. You would take your products over your reactants. And again, you would also obviously use the coefficients as the exponents and square, cube, or whatever it might be if you needed to do so. So you can use this equation and figure out, for example, under standard conditions, would a reaction maybe be spontaneous? But if you did something like play with concentrations or pressures, would that reaction still be spontaneous at that point? Again, Q like calculated like K, and again, normal things left out of it. Now, when we actually do get to sort of equilibrium conditions, the delta G in the above equation is 0, and Q would then be the equilibrium constant. And that gives us this other equation here that involves delta G, which is delta G is equal to minus RT natural log of K in this case. And this is still kind of the same stuff as above. This is our delta G in standard conditions, which means you pretty much could probably do your products minus your reactants, by the way. And that's the same as up here, products minus the reactants as to how you would do that. R is the same R. T is still our temperature in Kelvin. And obviously K is our equilibrium constant, right? That we should know. Now, what should you choose in these conditions? Again, at this point, we've seen sort of 4 different formulas that involve delta G. Once again, if you have just the equation given to you and you want to calculate the delta G or figure out if a reaction spontaneous, you could do products minus reactants. If you have H and S given to you, don't reinvent the wheel. Just use those and go into the one that has the H and the S in the formula. And obviously, if it's anything involving the equilibrium constant, this last one is the one that should use. Either you're asked to calculate it or you're given the equilibrium constant. And anything where they kind of give you pressures, concentrations, things that are not standard sort of conditions, then the top one is definitely the one to kind of choose. So that's what I said earlier, that probably the best route is based on the question that you're answering, kind of choose the delta G sort of equation that fits kind of the information that's given to you. Now, I will say a couple of mistakes that people make with these equations is people always want to subtract this one. Then that is a positive, so it is a plus. And people always maybe forget the minus on that one. So again, those signs you want to be really careful of. So those are very common sort of mistakes. The other thing, again, that you want to be careful of, as we talked about in a number of places, is again units. So with that R it being in both of these, it is in joules. And typically speaking, your delta G's here are going to be in kilojoules. So again, you got those unit differences that you got to watch out for. It will be compounded even worse if you do a little inverse of the natural log with the E and try to solve for it if you kind of mess those units up. So you really want to be careful on those. Any questions on that there? All right. So this equation we could kind of look at and think about the same way as we think about other equations. But truthfully, because there is the equilibrium constant in here, we pretty much could just think about our equilibrium constant that we know. So clearly, if we have a large value of K, that is going to give us a sort of positive value there for our K and that natural log K, and that will get us a negative value there for our G. So we would expect our reaction to be spontaneous, and because it's spontaneous, that means it should be going from reactants to products. We should have a lot of products. A lot of products means we should have a larger value of K. Opposite is true if we have a smaller value of K. That will probably turn our delta G into a positive value, which means that the reaction, the way it is written, is non-spontaneous, which means we would expect actually more reactants than products at equilibrium, and that's what will result in our lower K value. If it's somewhere around 1, we'll probably have a delta G that's equal to 0 because the natural log of 1 is 0, which will wipe out everything on that equation, basically. So it'll be relatively small. They're both equally sort of favored in a sense, reactants and products in that particular case. All right, let's try some here. What is the equilibrium constant for the following reaction? Here's some delta G values you can find from the table. Let me add O2 to the mix. That is 0 kilojoules. Okay, so let's take a look at this one. So like I said before, there's a number of sort of formulas that involve delta G. And the only one that really has the equilibrium constant in there is the one we just saw, which is delta G is equal to minus RT natural log of K. Here we do need to convert our temperature into Kelvin. So we got our Kelvin temperature. Remember, R is our constant, and we do want to use the one that involves energy, which is that. There we go. And in this case, we are looking for K. We don't have delta G, but we could go to the table and calculate delta G. And in this case, this is going to be a situation where we're going to do our delta G is going to equal our delta G of our products minus our delta G of our reactants in this case. So our delta G here will equal our products, which is 3 times 0, minus our reactants, which is 2 times our 163.4 kilojoules. That's going to give me a 163.4, and that's going to give me a negative 326.8 kilojoules in this case. We now have our delta G, we have our RRT, so we could use that to solve for what we need. Again, unit-wise, we do need to be careful because our R is in joules. So I'm going to multiply it by 1,000 to get me into joules in this case. That's going to give me the negative that's there as well, not to be confused with the negative that's over there. And that's really important. You got both of those negatives, 3.184, 298, natural log of K. So sort of cleaning up the left and right hand side here, that's going to give us on the left hand side, not that. It's going to give us here a negative 326,800 joules is equal to a negative 2477.572 natural log of K. We're going to divide that to the other side, not forgetting to also take across the other side our negative as well. And that's going to turn us into a positive number, which is really important. And that's going to give us a 131.9 equals the natural log of K. At this point, we could take E of both sides. So maybe I'll come up here and do it here. So 131.9 equals the natural log of K. We're going to E both sides there. And this is, again, why it's important you take care of the negatives there, because if you do it with the negative number, you're going to get a very different number. And if we do that there, that looks like a 1.9 times 10 to the 57 will equal RK, as those guys will cancel out basically in that case. Any questions on that one? Now, these things should agree with each other. So let's see if these things do sort of agree with each other. I hit me a negative delta G, which means this reaction should really be spontaneous and should be heading to our product side, which means I should probably have more products than reactants. And that means I should end up with a large value of K, which I would say that definitely qualifies as a large value of K. So again, those things should agree with each other. If you got a really small value of K here, then you know something probably went wrong, probably with some negative signs along the way. Any questions on that one there? Let's try a couple more here, I think. Calculate the delta G naught for the following reaction if the KSP is 1.7 times 10 to the minus 6. So see what you come up with here. Okay, so in this case, once again, we do have the equilibrium constant given to us, so that is a big hint that we should use the same equation there. And in this particular case, we actually do have everything over here. It doesn't really matter what type of K. Remember, they're all the same. Even though they have a little different subscript, they're all equilibrium constants, so you can put them into this equation. Doesn't matter what type. We have everything else we need, so we can just plug in. In this case here, we got a minus or 8.314 joules per Kelvin per mole. We do need to convert our temperature into Kelvin. So again, a 298 on that one, natural log of 1.7 times 10 to the minus 6. So if we do that there, times it by 298 and times it by 8.314, we're going to end up here with 32,914 joules, are about 32.9 kilojoules as our value here. Is this reaction spontaneous here? Would we expect reactants or products in this case? We should expect reactants, right? And that's because we should not expect it to be heading towards the product side. And that again agrees because we have really sort of a non-spontaneous reaction, which means it's really going to kind of hang out over here. We should have more reactants than products. And that does make sense with our K value, which is a small value of K, right? So that again, we got a negative value here for our delta G. It probably should not make sense based on the fact that this is KSP, which is a really small sort of K value to begin with. Any questions on that one there? All right, last one here. Delta G naught for this reaction is 2.6 times 10. No, 2.9, just 2.6 kilojoules per mole at 25 degrees. In one experiment, we had initial pressures of hydrogen at 4.26 atmospheres, I2 at 0.024 atmospheres, and HI at 0.23. We want to know what is the delta G in this reaction and predict which way this reaction should head. Take a few moments there and calculate that one up and see what you come up with. Let's take a look at this one. We're looking for delta G, and they give us a delta G naught. If they didn't give it to you, you might have to calculate it yourself, but in this case, they actually did. If you were going to calculate it, it would be your products minus reactants. This obviously means we have two delta G's, so we probably want to use the equation that has two delta G's in it, and it is this one here. Remember that this delta G is sort of, again, under non-standard conditions, and in this particular case, it is our pressures here. These are not all one atmosphere, so these are really sort of the non-standard part of this calculation. So in this case, we kind of have everything that we need. We again just want to be careful of units. I am going to multiply one more time here by 1,000 to convert this guy into joules. And again, this is a plus, not a subtract in this situation. And I did that because my gas constant's in joules, so I am not off by that factor that I don't want to be. 298 in this case, natural log of our Q. Now our Q is the reaction quotient like we've seen before. It is our products. And we do need to square it over our reactants. And once again, it is done just like we calculate K. So in this case, we would go in and we could also do it with pressures, which is what we're dealing with in this case. So if we go in there with our pressures, we will end up with 0.23 squared divided by 4.26 and 0.024. That's going to give us our Q in this case here of 0.51741, which we could pop into here. All right, now we got everything we need. I can clean up the right-hand side there, the plus sign. So I'm going to take the natural log of that number I just got. I'm going to times it by 298 and also times it by 8.314. That's going to get me a plus negative 1632.52. I'm going to take my 2.6 times it by 1,000, not 10,000, but just 1,000. That's going to give me 2,600 joules here. So I take my 2,600 joules and I add it to my minus 1632. That is going to get me about 967 joules, or 0.967 kilojoules in this case. First off, any question on the calculation there? This reaction should proceed which way? Yeah, this way, yeah. As we have a positive value here for delta G, which means this reaction is not going to really head towards the product side. It's going to hang out on the reactant side. And thus, we should also probably have a fairly small value for K if we were to calculate that as well. Any questions on that one there? Which, if we did calculate it, it would be a pretty small value, yeah. No, so it doesn't necessarily mean the endothermic or exothermic. Here we're looking at the delta G being positive or negative. Typically, if you have a delta G that's negative, it means it's going to be spontaneous, or you can think of it as heading towards the product side. If you have a delta G that's positive, it typically will be non-spontaneous, and you can think of it as like heading towards the reactant side or just kind of staying on the reactant side. Yeah. Yeah, so there are other factors. Obviously, the S and the can play a role as to whether or not you have a positive or even with a positive delta H, that you could still have a spontaneous reaction. Other questions? All right, that is this chapter, thermodynamics in the books. Yeah. All right, we will lay it up there.